Imagine finding a star that's mathematically older than the universe itself. Seriously. If you've seen the viral headlines out there claiming astronomers found something that completely breaks physics and rewrites cosmic history, well, this is it. It's called HD 140O283, but most of us know it by a much cooler name, the Methuselah star. Today in this explainer, we're going to look at the raw data, break down the astrophysics, and solve a paradox that has literally kept cosmologists awake at night.
I want you to really ask yourself for a second, is it physically possible for a celestial object to predate the very fabric of time and space? Logically, no way, right? You can't exactly have a star before you have a universe for it to exist inside of. But for a while, the observational data we were getting from our most advanced telescopes suggested exactly that. We were looking at a star that seemed to completely defy the fundamental chronology of existence.
Just look at the sheer paradox we're dealing with here. On one hand, we've got the widely accepted age of the universe, rooted in the Big Bang model and cosmic microwave background data, sitting at 13.8 billion years old. On the other hand, we have the Methuselah star, hanging out right in our own galactic neighborhood, and it's estimated by some calculations to be over 14 billion years old. You really don't need a degree in astrophysics to see the problem here. It's kind of like meeting a teenager who claims to be older than their own parents. So how do we solve this? Well, we have to investigate both sides of the equation.
Let's start with Section 1, Suspect 1, the Methuselah star, investigating HD 1400283.
To solve this detective story, we first have to understand how astronomers actually figure out a star's age in the first place. I mean, they don't exactly come with birth certificates. Instead, scientists look at their metals. Now, I need to clarify something kind of funny here. To an astronomer, a metal is literally just any chemical element heavier than hydrogen and helium. Since hydrogen and helium make up more than 98% of all the elements in the universe, astronomers basically consider the rest of the periodic table a rounding error. But the amount of these heavier metals inside a star, that's the absolute key to unlocking its age.
And this brilliantly illustrates exactly where Methuselah fits in. Think of the universe's history as a succession of stellar generations. Right after the Big Bang, you had the very first stars forming from pure, primordial hydrogen and helium. We call these population 3 stars. They had absolutely zero metals. And because they lacked those heavy elements to moderate their fusion, they were massive, like up to 10,000 times the mass of our Sun, and they lived incredibly short, violent lives, eventually exploding as supernova and seeding the cosmos with the very first heavy elements. Then came population 2 stars, which formed from those slightly enriched gas clouds. They have very low metal content. And finally, much, much later, you get population 1 stars, like our own Sun, which are rich in heavy metals. Methuselah? It's a population 2 star. It formed right after the massive, metal-free population 3 stars died, but well before metal-rich stars like our Sun ever existed.
So the crucial point here is that while Methuselah is undeniably ancient, it's a true population 2 relic from the early cosmos, the unbelievable 14 billion year figure is actually the result of massive margins of error in stellar age calculations. Determining the precise age of a single isolated star is notoriously difficult. The math depends heavily on super precise measurements of its distance, its exact luminosity, and some really complex models of nuclear fusion. When you factor in the margin of error for all those variables, that 14 billion year number has a lot of wiggle room. It could easily be younger. But wait, actually, scratch that. That's only half the paradox. What if our measurement of the universe itself is wrong too?
Which brings us to Section 2, Suspect 2, the universe's age crisis and the Hubble tension.
Let's move over to our second suspect, the age of the universe, which, by the way, is currently undergoing a massive crisis in cosmology. You see, the 13.8 billion year age isn't just some random guess. It's tied directly to something called the Hubble constant. Think of the Hubble constant as a cosmic speedometer. It tells us exactly how fast space itself is stretching. Coined by Edwin Hubble back in 1929, this number is absolutely essential. The idea is, if you know exactly how fast the universe is expanding today, you can theoretically hit rewind and calculate exactly how long it's been expanding since the Big Bang. But here is where the problem starts. Enter the famous Hubble tension, when cosmologists measure the expansion rate by looking at the cosmic microwave background, which is basically the relic radiation from the very early universe. They get a highly precise speed of about 67.4 kilometers per second per megaparsec. But when astronomers measure the late, nearby universe using local stars and supernovae, they get a significantly faster speed,
around 73 or 74 kilometers per second per megaparsec. So we've got two different methods looking at two different epochs of the universe, giving us two totally conflicting speeds.
Now, why this matters for our explainer today is pretty simple. If the universe is expanding faster than those early universe models predict, it means it reached its current size more quickly. And that would actually mean the universe is slightly younger than 13.8 billion years, which, as you can guess, would make the Methuselah star look even more impossibly old, threatening to completely break our standard cosmological model.
However, incredible new data from the James Webb Space Telescope just provided a huge breakthrough. An analysis led by cosmologist Wendy Friedman used JWST's stunning resolution to essentially cross-examine the evidence. Instead of relying on just one type of star, her team checked 3 different, independent types of stars across 10 nearby galaxies: Cepheids, tip-of-the-red giant branch stars, and carbon stars. By combining all these independent methods, they pinned down an expansion rate of exactly 70 kilometers per second per megaparsec. This number sits right in the middle, and with the margins of error, it overlaps perfectly with the early universe models. So it turns out our standard model of the universe isn't broken after all.
Let's wrap this up in Section 3, Resolving the Impossible, when uncertainties overlap.
Okay, let's bring the two halves of our investigation together. We have the Methuselah star with its questionable birth certificate, and we have the universe's age firmed up by the latest James Webb data. When you combine the massive uncertainty in the exact dating of a population 2 star with the refined margins of the universe's age based on this new Hubble constant data, the math actually overlaps. Take a look at the caveat here. The 14-plus billion-year age for Methuselah is an absolute upper bound, pushed to the extreme limit by observational uncertainty. When you calculate the lower bound of that error margin, the star's age safely drops below 13.8 billion years. It neatly tucks itself right into the timeline, just a few hundred million years after the universe was born.
So the ultimate takeaway you should remember here is that physics isn't broken. Our standard cosmological models are absolutely still holding up against incredible scrutiny. This ancient star didn't exist before time itself. It was simply born in the Dark Ages right after the universe began, inheriting the sparse heavy elements left behind by those massive, fast-burning population 3 stars that came just before it. It's an incredible survivor of the early cosmos for sure, but it obeys the laws of time just like everything else.
As we close the case on HD 140283, it really leaves us wondering what other mind-bending anomalies are waiting for us out there in the earliest epochs of time. With telescopes like James Webb now peering deeper into the cosmic dark ages than ever before, revealing massive galaxies forming much earlier than we ever predicted, we have to ask, what other universe-breaking paradoxes are we going to uncover next, and how will they force us to rethink our entire place in the cosmos?